Greetings and salutations. Welcome back to another Ocean Protect webinar. Thanks for everyone for joining us. Sean, how are we?
Good, Brad. Always good to be on board with these webinars. Obviously, big fan of these.
You should be, because you do a bunch of them, and this is actually the third. And third of this year. I think you've done. This will be the sixth total, I think, off the top of my head, and this will be the last of 2025. We'll hear from Sean. So I've got a little bit of a tear in my eye,
but I guarantee I'll be in most of them for the rest of the year. Though I've registered for all of them last year as well. So yeah.
The old smooth talker. Look, and this is obviously the fourth of our webinar series for this year. Sean's going to talk about rainfall and obviously he's already done the stormwater channel design webinar, the GIS of stormwater engineering, and then if you can't get enough of Sean's dulcet tones today, you can actually jump on the oceanprotect.com.au website under webinars, and you can hear the recordings of Sean's previous slides. And if you already are subscribing to the newsletter, you probably got your finger on the pulse of all the stuff's going on, whether it's a Sean Quilty webinar or something else. But feel free to jump on the website or newsletter to make sure you got your keeping abreast of everything coming up. And I think that might be. Oh, just a reminder, folks, before I introduce Sean, if you do have any questions, please put them in the Q&A panel. Sean's going to do a bit of a song and dance routine to critical acclaim, and then we're going to open up the Q&A with you guys. So feel free to post your questions in the Q&A. First come, first serve, essentially. Just a reminder, as always, the recording and the slides from Sean's preso today will be made available at that website you can see there. And we always get a whole bunch of CPD form requests, and I think we've streamlined this process now. So you should get a CPD proof or form very soon after this webinar, at least within the week. But if you haven't, just email marketing@oceanprotect.com.au. Cool. But without further ado, I might pass you over to my esteemed colleague in the biz, the stormwater industry, Sean Quilty. And after that, you're familiar with Sean. He's a legend. Needs no introduction, given us his third webinar for the year. But he's a superstar engineer, a wealth of knowledge, whether it's Pitch Black Consulting or Quilty Engineering Hub or wowing the students at TAFE Queensland. He's a fountain of knowledge, and I'll pass you over into his tender care. So Sean,
Thanks,
take it away.
All right, just give me 1 sec to share these screens, and we'll get stuck into it. All right. So today we're going to be looking at stormwater rainfall, and so we've obviously we've had a fair few. Oops, I better not be doing the same thing it did last time. We've had a sorry, we've had a fair few webinars, and yeah, we've had a fair few webinars, but this one really just brings it back to the fundamentals when it comes to rainfall itself. So there's a bit of terminology. There's a lot of different sort of terms that we use. So this is hopefully going to try to sort of clear up all the different fun sort of terms that you might hear around the office or around the industry. And really, this is something that, in my opinion anyway, definitely all our engineers, but certainly all of our designers as well, all the civil designers working on any sort of road design, any sort of stormwater infrastructure, you've really got to have your finger on the pulse when it comes to the terminology that we're using. Know the difference between AEP and ARI, just real simple sort of things. So that's what we're going to do today. We're going to run through rainfall, and it is really that real high level introduction into, I guess, how we talk about rainfall itself. And then right at the end, we'll just start to touch on a bit more of the specifics. We'll explain what a hydrograph is, and then explain some the ARR Ensemble Method. So this is like a new approach to stormwater design, stormwater analysis that's sort of just been brought out in the more recent sort of years. So it's just that fundamental awareness, I guess, that we're going to really focus on. All right, so we're going to start with design storms. So when we think about rainfall seems to be, on face value, it's pretty simple. It rains, water falls from the sky, and then it'll basically run off our catchments, but it's actually quite complex when you look into it. Rainfall is extremely variable, so it can be very random, whether, when it takes place, where it takes place, how it, physically falls from the sky as well. You can have micro bursts within larger bursts within complete storms. So it's super complicated when you actually look at physically what's happening. And so what we need to do is we need to simplify that. Civil engineers, civil designers, we've got to try to simplify the process so then we can actually make the calculations and do it in a timely sort of fashion as well and be efficient in what we do. So this is going to explain how we sort of simplify rainfall itself. And that's where we get into these design storms. So a design storm is essentially, it's just a hypothetical rainfall event. So we're trying to simulate the natural rainfall events themselves. And the way that we do this is we will base all of our analysis, if you like, on historical rainfall data. So we'll actually collect a bunch of sort of rainfall gauges, I suppose. So every time it does rain, we'll monitor how much water falls from the sky and how that happens over a period of time as well. And so that rainfall is going to fluctuate, or the intensity is going to fluctuate. And so there's literally, thousands and thousands of recordings that we've been taking over decades now. And so that's what we use as the basis of these design storms. So then we look at the storm itself. And again, like I said before, they can be pretty random and it's very hard to, specifically depict what a storm's going to do. So this is where we try to break up any storm into small sort of portions, I suppose, or sections within the storm itself. So we do this by looking at, in this graph, for example, we've got time on the x-axis and rainfall depth on the y-axis. So you can see over time, your rainfall is going to change, it's going to fluctuate. And it is quite random. It's not always just a nice incline and then decline. It can sort of peak multiple times. There's all sorts of stuff that could happen. But within that, we try to break it up into, we've got a pre-storm. So when it rains and then it stops, and then we'll classify it as the next storm. But then we have what we call the complete storm, which is broken up into a few parts. And we'll look at that in a couple of minutes. So this is the complete storm that we're looking at. And this will include the build-up, the peak, and then the eventual decline of the storm itself. So this is how we start to basically take all of that historical data, and then we start to sort of chop it up into more manageable sort of pieces. So if we take a complete storm, we then break it up into three parts. We'll break it up into a pre-burst portion of that storm, a storm burst, and then a post-burst. So the pre-burst is a period leading up to the peak intensity of the rainfall. So it's typically it's a smaller intensity, if you like. There's not as much rain falling from the sky during a pre-burst. The storm's still developing. But what's important to note is this pre-burst will actually start wetting the ground itself. So if you've got say a natural catchment, so it's vegetation, grass, soil, that pre-burst will actually start saturating the ground. And that's really important to note because the more saturated the ground becomes, the more excess runoff you're going to have. Because if the ground's completely saturated, any water that hits that ground is then just going to run off straight away. It's not going to be able to soak into the ground itself. So pre-burst is really important to understand. So going on from pre-burst, we then look at the storm burst. So this is where the peak of the storm event actually occurs. It's where your rainfall intensity is going to be at its maximum as well. And it's where you'll find the highest volume of rainfall that will occur. So when it comes to designing infrastructure, if you're designing roads, if you're designing stormwater pit and pipes, if you're designing culverts, any of that design is always based on the storm burst itself, especially if you start looking at more simplified hydrological models. So if we start thinking about the rational method, if we go back to a few webinars ago when we talked about the rational method, all of that is based on the storm burst. Later, we're going to talk about IFDs, intensity, frequency, duration tables. And that again refers specifically to this storm burst. It's not the complete storm, it's just this high intense sort of portion of your complete storm itself. And then finally, we've got the post-burst, kind of similar to the pre-burst. The peak intensity is gone, and then you've just got this diminishing rainfall that's still dropping from the sky, but not as at a high intensity. So that's your complete storm. That's how we break it up: pre-burst, storm burst, and post-burst. So now that we understand that we create these design storms, if you like, so these, I guess, synthetic storms that we create based on historical data, there's two things that a design storm needs. It needs a storm frequency and a storm duration. And then you'll be able to then state what your design storm is. Is it a 1% AEP with a 30-minute duration, for example? So it's got to have the two things combined to describe a design storm. So when it comes to storm frequency, we're trying to explain or depict how frequent this particular design storm will occur. How often are we going to see this design storm? So we break these storm frequencies into a broad group of classifications. So you can see here, we can call it a very frequent storm. So something that you would see pretty much every single year. You'll have a couple storms or a few storms, say in summer. That's what we would call a very frequent storm. We then go into frequent and infrequent storms, and then we get into the rare, extremely rare, and extreme storms. So if we were looking at tropical cyclone Alfred that just hit southeast Queensland a few weeks ago, I'm not sure exactly the numbers, but that's where you start looking at, say, an infrequent storm event. I don't think it pushed into the rare, but it was definitely infrequent. So that's how we start classifying these different storms. I'd just like to point out as well, because especially if you're new to rainfall, you'll start to pick up different guidelines, and you just want to watch out because there are some slight discrepancies in how certain guidelines describe the storm frequency. So whether a storm is classified as frequent or infrequent, for example. So there are ARR guidelines, Australian Rainfall and Runoff guidelines. There's the ARR Data Hub, where you can get your temporal patterns from, and I'll show you that in a few minutes. And then there's a Bureau of Meteorology Water Frequently Asked Questions website. Now, each of these sources will actually have a slightly different take on the storm frequencies. So it's important just to know that terminology, because when somebody's talking about a frequent storm, you might be talking about an infrequent storm. But what I've got here is, this is taken from the BOM website. So typically this is where you'll get all of your IFD data. And so here it's a table that basically shows you the storm frequency. Now, on the left column, you can see the frequency descriptor, as they call it. That was the very frequent, rare, and so on. That was the terminology we were looking at. But you can tell that's not really tangible. You know, that's not really giving me an exact number necessarily. So that's where we start looking at different units. And in this case, we look at, we can call these storm frequencies in the sense of an exceedance per year, an EY, an annual exceedance probability, or an AEP, or an average recurrence interval as an ARI. So they all mean the same thing. They're telling you how frequent your storm is likely to occur on average over a length of time. The exceedances per year, so those values refer to the number of times an event is likely to occur or be exceeded within any given year. So as an example, if you had a design storm and it had a value of a 4 EY, 4 exceedances per year, you're likely to see that storm 4 times within the year. So if you sort of spread that out on average over the year, that might be every 3 months. Every few months, you'd see this particular storm. So that's showing you that's very frequent, right? If you look at your values, or as we sort of go through here, very frequent storms typically use the EY unit. When you go into frequent all the way up to extreme, we start to look at AEP, the annual exceedance probability. So this is a percentage, the value, and it's the probability of an event occurring or being exceeded within any given year. And so what that means, if we had a 1% AEP, that means that that storm is, it has a 1% chance of occurring in any given year. So it relates back to like a Q100 design, I suppose, but a 1% AEP storm could happen this year, and there's a 1% chance on average that it might happen this year. Then we have the average recurrence interval, or ARI. So if we look at that 1% storm, for example, that has an ARI of 100, which means it's a 1 in 100 year likelihood that that storm could occur. Now, I've got to really stress this. We do not use ARI anymore. It's still in council planning scheme policies. There's a bit of a legacy. It still hangs around in a few documents here and there. But in the industry now going forward, we always try to use AEP wherever possible instead of ARI. The reason being the ARI terminology kind of gave us a bit of a false sense of confidence, I suppose, or security, because a lot of people would, not from an engineering background, they would hear a 1 in 100 year storm. And if we had that 1 in 100 year storm this year, then people would think that they're okay for another 99 years before that storm hits again. Now, we know that is definitely not the case. In fact, what it means is this year, you've got a 1 in 100 chance of having that storm. Next year, you have the same 1 in 100 year chance. So you could have this storm in any year. It's not, obviously it's quite random and quite variable when we talk about rainfall. So just keep that in mind. Do not use the ARI, always use the AEP. That's what we want to use going forward. Unfortunately, a lot of the media still uses the ARI, which is really annoying. And there's many articles that I just laugh about, but it's still pretty dangerous, where they'll talk about the 1 in 100 year storms, and they'll sort of say, we're right for another 99 years, nothing to worry about. But obviously that's pretty misleading. Anyway, that's the storm frequencies, and that's how we can sort of classify those. So now we get into intensity, frequency, and duration tables. So when we're looking at any sort of stormwater design, we need to understand what the rainfall intensity is. So how much water is actually falling from the sky. So this is where we use IFD tables, and we can obtain our rainfall intensity. So in this example here, these values are in millimeters per hour, but your IFD tables can be represented as just millimeters. So a depth of rainfall for your duration, or it can have a rate, millimeters per hour. So when you get an IFD table, they're the values you're going to get or obtain. But before you can obtain your rainfall intensity, for a design storm, we need two things. So I mentioned this earlier, we need to understand the storm frequency, and then we need to understand the duration. You need both of those things to be able to label a design storm, if you like. So there's no point in saying it's a 1% AEP without giving that duration as well. Otherwise, it doesn't really mean much. It's only telling half the story. So in an IFD table, and I'll show you where you can get these as well, you'll see the probability, which will be up the top. It may be AEP. It may also show you as an EY as well. And then on the left-hand side, you'll see that there's the storm burst duration. So again, I mentioned before, when we look at a storm, we have the complete storm, but that storm is built up with or made up of the pre-burst, the storm burst, and then the post-burst. These durations are referring to the storm burst. It's not the complete storm itself. It's just that intense middle part of the storm. So with each of those, the duration and the storm frequency, you can then obtain your rainfall intensity. And that's what you'll plug into all of your calculations for stormwater design and road design as well. So if you need to obtain IFD data, the Australian Bureau of Meteorology has a website where you can obtain IFD data from anywhere around Australia. It's free. You can just enter the website and then punch in your values, and away you go. You don't even have to sign up for anything, and it's all publicly available. So it's they call it the 2016 IFD. So that's when they updated a whole heap of rainfall data. And so it provides updated design rainfall estimates, again, anywhere across Australia. When you download this or when you access this website, just keep in mind that the rainfall data can be displayed in millimeters or millimeters per hour. So just double check your units before you start using any of those in your calculations. So all the values that you see are derived from observed rainfall data, and they do a heap of statistical analysis in the background, different statistical techniques, until they get all that historical data and then give you a bit of an average rainfall intensity for each of these durations and frequencies as well. Just important to note that any of these values that you obtain from the website does not include any effect for future climate change. And we'll talk about climate change in a minute. We do have to incorporate climate change in our design going forward, but these websites don't do that for you. You have to apply that after the fact. So I've got a couple of websites there. The first website is to access this IFD data. Again, free, publicly available. And then the second one is just some frequently asked questions. So I'm hoping we get heaps of Q&A at the end of this session. But if there's anything that we didn't quite answer, that's probably a good spot to go to, because there's quite a good summary of questions there as well. All right, climate change. So I think most people are aware of climate change and what's actually happening with our world currently. But just to sort of recap, we can see the climate is definitely changing, and at a pretty scary rate. So essentially, our global temperatures are increasing due to greenhouse gases, and that's messing around with our hydrological cycle. So there's the rainfall that we're talking about. When it rains, it's actually doing a little bit strange sort of things that it hasn't really done in the past. So this climate change or the increase in greenhouse gases, it's resulting in intensifying our rainfall and our extreme weather events. And the way that it does that is that because the atmosphere is warming, it actually makes or increases the water vapor within the atmosphere. And so that changes the rainfall patterns that we're looking at. And it also changes the soil conditions that we deal with as well. So a big part of stormwater design is not just when the water falls from the sky, but it's also assessing what it does on the natural ground as well, how the soil starts to soak up and take some of that rainfall. And that's obviously going to change with climate change. So essentially all the science and all the research that's out there, it's showing that we're looking at increased rainfall intensity. And in particular, we're looking at much shorter and more intense rainfall bursts. That's where we're seeing the biggest change in these patterns. So the problem with this is all the infrastructure that we're designing, so civil designers, civil engineers, civil draftspeople, we're looking at roads, bridges, stormwater, and even sewer as well. And all of that is being affected by these sort of more recently experienced, more frequent and more severe storms. On top of that, with climate change, we're looking at rising sea levels. We can see just over the last decade that the sea is rising faster than it ever has in the past. And so that's resulting in a lot of coastal flood issues as well. So we're kind of getting it from both ends. We're getting more water that's falling from the sky, and then at the same time, our sea's coming up as well. So we've got this little band that we're trying to work and design with, and yeah, we're just getting sort of pinched on both ends. So it's a pretty big issue, and it's something that we've got to try to figure out quite quickly how we're going to tackle this. The Australian Rainfall and Runoff Guidelines, they provide guidance, and essentially the way that we've got to go going forward is to focus on resilient stormwater infrastructure and just infrastructure in general, I suppose. So in the past, prior to climate change, it was pretty simple. The past ARR guidelines were quite simple as well. You'd look at your design storms, and then you'd build your houses, you'd build to a certain freeboard, and you were okay. And that was on the premise that we were safe from any sort of, flood impacts. Now we know that it's very unpredictable, and we don't really know what it's going to be like in 10, 20, 50, and 100 years. So now we've got to change the way that we're thinking from an engineering perspective, and we've got to look at resilience and building resilience into our design. So instead of trying to build a house that's above all of our floodwaters, we now accept the fact that our house will be flooded. And so we've got to build a resilient house, if you like, to, I guess, be ready to experience that, because we know it's going to happen. It's not an if, it's a when. So anyway, that's a bit of a different take on engineering. Certainly different to when I started 20 years ago. This resilience is definitely a big part of what we do now. So when it comes to climate change, and there's a fair bit here, but I know this will be recorded and shared, so you'll be able to sort of go back, hopefully. But essentially, when it comes to rainfall, we've got these climate change factors that we apply to our rainfall intensities. So these factors basically just means you increase your rainfall intensity for the values you might be designing with. Now, to get to those to get to the climate change factors that we apply to the rainfall, there's a bit of I guess you're trying to predict what's going to happen in the future. So the way that this was done, this was based on shared socioeconomic pathways, essentially looking at 5 different scenarios to see how this climate is going to change over the next 100 years. And it's 5 different sort of paths that we might be able to take. I won't go through each one of those, but essentially SSP1, and as you start, the lower the number, the better or the more optimistic the pathway. So if everyone around the world, all the politicians, all the movers and shakers, all the leaders basically started 5 years ago and said, yep, all right, we're going to cut all of our pollution. We're going to control all of our, stormwater pollution. We're going to control all of our fossil fuel, greenhouse gas emissions, and did everything we possibly could. That's the best outcome. So that's one pathway. That's one avenue that we might take. And if we did that, you'll see that the climate change factors, they won't be that great, because rainfall won't be impacted as much, because your greenhouse gases aren't going to be as severe, essentially. As we go through each of those, all the way up to SSP5, this is sort of working right up to a worst case where we have huge economic growth. Everyone's, getting stuck into the fast fashion. We've got brand new outfits every weekend. We chuck them all out on landfill. Keep, mining all the minerals, all fossil fuel focused. If we go down that path, it's going to be a very different future in the next 10, 50, and 100 years. And so that'll have a completely different prediction of how the climate will be. And so that will give us some different factors. So there's all these different pathways that we might take, and we're not really sure where we're going to go. So out of those pathways, we can then, and this is all science and analysis that's already been done. So we look at the pathways and we say, all right, well, what is the greenhouse gas emissions going to look like in each of those pathways? And so essentially there were 4 representative concentration pathways, RCPs, that were looked at. You can see the year from 2000 to the year 2100, and then each of these pathways. The smaller the number, the more optimistic or the better we are at trying to control climate change. The larger the number, the worse we are. To the point where if you look at RCP 2.6, the green line that we've got here, it shows if we do everything that we can and we work together, collectively, greenhouse gases are going to continue to climb till about 2050 2050, 2060 maybe, and then they'll actually start to decline. We'll actually reduce the amount of greenhouse gases. And if we did that, then our climate change was sort of getting worse, but then we'll actually go back and start improving and repairing the atmosphere. Until we look at RCP 8.5, for example, the worst case. Now, this is business as usual. We don't change anything. We continue doing what we have been doing the last sort of 10 to 20 years. And you can see that just skyrockets. We just increase the greenhouse gases by a stupid amount. So with each of those paths, we've got 4 different sort of scenarios played out. So then we come into looking at what that actually means with regards to a warming atmosphere. So in here, we've got the year on the left-hand side. This is all based off of the Australian Rainfall and Runoff Data Hub. And then we've got our 4 scenarios, our best case being SSP 1, 2.6, and our worst case being on the far right, SSP 5, 8.5. So you can see how much the temperature is going to change. So our best case, 1.2 to 1.5, and then it starts dropping back off to 1.4 at the year 2100. Worst case, you can see the atmosphere is going to rise by 4.5 degrees. Now, there's heaps of literature out there. I don't have to probably tell everyone that's online, but if we saw a 1.5 degree increase, that's pretty bad news. A lot of really bad stuff's going to happen in the world. If we saw a 2 degree increase, I think everyone was really starting to freak out. So if we had a 4.5 degree increase in the atmosphere, like God only knows what the world's going to be like, we probably won't be here to even talk about it, to be honest. And also pointing out that increase is an average temperature change, which means the sea level rises, land temperatures rise as well. Because there's so much ocean, it kind of skews that number a bit. So whilst the whole world might warm up by, say, 2 degrees or 4 degrees, the land-based temperatures will rise much more than that, and the sea will be a bit less. So that's why it kind of skews those values. So it doesn't sound like a lot, but in fact, it'll have devastating consequences. Anyway, from those changes in atmospheric temperatures, that then gives us an opportunity to get a factor that we can multiply by our rainfall intensities. So the rainfall intensity that we had 10 years ago is now more intense today. And in 10 years' time, it's going to be even more intense again. So the ARR Data Hub, and I've got a website there for everyone as well, that's where you'll be able to obtain these factors. And you basically just take that number, multiply it by your rainfall intensity based on what year you're trying to predict or what year you're designing to. So typically for stormwater pit and pipe or stormwater culverts, we're designing for a 100-year design life. So we should be looking way out beyond year 2100 and beyond. Some councils, I know Brisbane City Council, I believe we need to design for a 150-year design life. So we're going even further than what we can even predict for climate change. So keep that in mind. And yeah, I'll be interested to see once people start crunching these numbers, designing roads and pipes, and then all of a sudden you've got to apply a factor of 50% more up to 80, almost 90% more rainfall. Just see what sort of happens and how we manage that. So they're the climate change factors. You multiply them by your rainfall intensity, and that'll give us our best guess as to what might actually happen in the future. All right. So this was just going to sort of lead into a little bit more detail when it comes to rainfall. Now, if you were just starting out in rainfall, I'd encourage you to start looking at the rational method. That's always the best way to get into hydrology. It's the simplest hydrological model, very easy to follow, really simple equation. But one of the limitations that you have with the rational method is that it's only a split second in time that we're looking at it. So we're not really looking at rainfall over a duration necessarily and monitoring how that rainfall changes or how your peak discharge is going to change over time. It's really just that snapshot as a worst case. If you needed to look at a time-based analysis, or if you needed to look at water volumes, if you need to look at detention, that's when we start to get into the world of hydrographs. So this is just a little bit of terminology, just in case you start hearing about these things. It'll hopefully give you a bit of an idea or a bit of an insight into how you can get started. So when we look at rainfall, we need to understand how that rainfall is going to drop from the sky over a certain period of time. And so we do that by using temporal patterns. So a temporal pattern defines the distribution of rainfall as a percentage over time. So here we've got just a random storm, and we're saying this is for I think 45-minute storm. So each one of those bars that you see, that's a 5-minute time step that's going through. And so we're saying in the first 5 minutes, 5% of the rain is going to drop, and then a little bit less, and then it starts ramping up until we get to the peak, and it's about 22 or 23% of the rainfall is going to drop. But it's the burst proportion that we're looking at. So again, we've got the complete storm, but we're just chopping out that storm burst section. And out of that, we're going to see how that storm burst occurs. And we can see here how it kind of fluctuates. But again, just a percentage. So we're not looking at actual depths or anything yet. And that is what we call a temporal pattern. So that's a certain pattern that a rainfall might fall. If you think about all the historical rainfall events that we've had over decades and decades, there will be millions of these temporal patterns, different ways that the rain has actually fallen. So it's very, very random. There's lots of different patterns, if you like. But then as designers and engineers, we've got to be able to pick out a certain pattern and say, this is our best estimate as to what might happen for our design storm. Then we have hyetographs. So this defines the rainfall pattern. But now we're looking at the rainfall depth or the rainfall intensity and how that varies over time. So again, we've got our bars, if you like, or our time blocks. So we refer to those as time steps. So if you imagine these are a 5-minute time step, we can see that instead of a burst proportion, a percentage of the storm burst, we're actually looking at a physical depth. So that will be dependent on getting your IFD data, for example. You might have an average rainfall depth over your 45-minute storm, but then you can sort of chop that up based on the temporal pattern, and then you can get specific rainfall depths for each one of those time steps. So now you can imagine if you had that and you were modeling, you're in some sort of stormwater software and you were modeling this, you could see that if you had a catchment and then that first 5 minutes dropped 4 millimeters of rain, you could then start to understand how much water would start running off that catchment. And then the next 5 minutes, more drops, and it's different rainfall depths as you go through. So that's how you accumulate all of this rainfall that's falling from the sky onto your catchment. So if you want to create a hyetograph, you need two things. First, you need a temporal pattern. So that was the percentage distribution of rainfall for a particular design storm. And then you need to multiply the temporal pattern or the distribution by a storm burst rainfall. So that's where you get the rainfall depth from, say, the BOM website. And then you multiply the two, and that will give you your hyetograph. So I've got a couple website links there again for everyone online. The ARR Data Hub at the top, again, free. You don't have to sign up or anything. You literally just plug in your location and you can download a whole heap of really useful rainfall data. And then you can get your IFD data or your rainfall intensities from the BOM website, that bottom image there. So once you've got your hyetograph and you have your catchment, then you can actually essentially model the water dropping from the sky, hitting the catchment, and then starting to run off and then ending up at your outlet of your catchment or the bottom part of your catchment. So that's where we run some pretty simple calculations, or the computer software will do it for us. And we will then create the same time steps at every 5 minutes, say, but we'll be able to see what the peak discharge is for each one of those time steps. So that will be dependent specifically to the catchment. If you have a different catchment, you'll have different peak discharge. So once we plot this, this is what we call a hydrograph. So it's basically looking at the outlet of your catchment, so all the water that's running off of your catchment, and how that discharge rate changes over time. So a couple of things that we're really interested in, typically it's that peak flow rate. So when does the peak discharge the most amount of water run off the catchment? So we want to know how much that is, the value of the peak discharge, but also the timing as well. When does it actually occur? And the other thing that's pretty important to understand is the volume, the sheer volume of water that's going to be running off for any given design flow. All right, so then this finally brings us to the ARR Ensemble Method. So that, and I don't expect everyone to be able to follow that if that's the first time you've seen hyetographs, temporal patterns, or hydrographs, but that's essentially what we do. Now, when we create, say, a hydrograph for a catchment, previously, when we used the older version of ARR, so ARR 1987, we used to just apply one single rainfall event. So if you were looking at, say, a 1% AEP storm frequency with a 45-minute duration, so that's your design storm, you would look at one temporal pattern, so one way that the rain can kind of fluctuate over time, and then you would use that one single temporal pattern to represent any design storm going forward for a 45-minute 1% storm, for example. Now, we know that the rainfall that occurs is not going to happen with that same pattern. It's not going to start at a certain rainfall intensity, then peak, and then drop off and do that every single time. We know it's completely random and there's a lot of variables in there. So what we now do with the current ARR version is we apply an ensemble, a group of rainfall events or rainfall patterns. So this is the ARR Ensemble Method, and this is what we should be doing basically with well, certainly with any sort of runoff routing, any detention basin sizing, anything like that, we'd be using Ensemble Method. So the way that we do that is previously we would just have an AEP storm frequency. We'd put in all our inputs and we'd basically just run one hydrograph, essentially, find out how much flow is running off of that catchment. But now what we do is we enter in an ensemble, a group of temporal patterns. And in fact, we enter 10. So we'll look at 10 different ways that that rain can fall from the sky for every single storm burst, for every single AEP that we're trying to design for. So any design storm we have, we'll actually run 10 different iterations of how that rain might fall from the sky. So obviously there's a heap more work involved, but luckily computer software does a lot of that for us. And then out of those 10 different scenarios, if you like, we then pick the average of those, or I guess our best estimate as to what most of the storms will sort of fall into. So that's the ARR Ensemble Method. There's a little bit involved in there, but obviously we're just trying to give you a bit of a small insight into rainfall, I suppose. So hopefully that gives you at least a little bit of information to start scratching the surface when we look at rainfall. It can be quite simple depending on what model we're using, like the rational method. Then it gets a little bit more complex when we start looking at time area methods or runoff routing methods, and obviously more complex again when we start to get into flood modeling. So I think we're doing all right for time.
Certainly are, Sean. Thank you very much. The questions have started rolling in already. There's been some very patient individuals. I'll kick off with a question from Rowan from East Gippsland Shire Council. Rowan asks, wondering with climate change and soil much drier, will it help to saturate reducing flow or make it more smoother so downstream flow will be higher?
Yep, good question. So based on the current science that we've got, climate change may make the soil drier, which in theory might allow more infiltration. But that change depends on where we are in the world. So for example, if we're looking just Australia, we've got our tropics in the north. We've got a very big arid sort of portion in the middle of Australia, and then obviously temperate down the bottom. Those soil conditions are going to be different all the way through those zones. So we can't just say that all soil is going to be drier, because it's not necessarily the case. And then the other thing is, if your soil is a bit dry and can take a little bit more infiltration, the flip side to that is we know the rainfall intensity is going to be much greater. And so you've got to see, are we able to soak up as much water as what the increase is falling from the sky? And the answer to that is no, we definitely not. We're going to get much more water falling from the sky, and any more infiltration that we can get in the soil is going to be much less than the excess water. So it's painting a pretty dark picture for us. It's not looking good. The other thing with dry soils as well, and I'm not a soil expert or anything like that, so don't quote me, but when you do get really dry periods, like in a drought, say, the soil itself won't actually soak up as much water. It's not like just a dry sponge and it just soaks up. Sometimes you'll get the soil, the surface itself and the soil itself will actually repel water, even though it's bone dry. So especially after, if you have a really bad bushfire, for example, and all that soil is basically just completely baked, you could have a rainfall event, a few weeks later, and a lot of people think, oh, well, we just had a bushfire, it'll just soak all that up. And the opposite actually happens. And it's almost like hitting, a sheet of concrete, and all that water just runs off straight away. So it's a pretty complex thing that we've got to analyze. But there's definitely ways that we can model and use sensitivity checks to actually see how that is impacted for sure.
Cool. Another question from Rowan regarding climate change as well. There's a lot of questions on climate change, Sean. Rowan asks, for sea level rise, is backflow valves the only practical engineering solution for a coastal town, or any other suggestions?
I would say backflow prevention devices are a backup. I wouldn't be relying on it solely, only because it's only a matter of time when you have your peak storm event occurring at the exact same time as a king tide, for example, or a cyclone hits, and then you've got storm tide inundation as well. And when those two hit, then all of a sudden your stormwater system is just, it's out of order. It doesn't work. So you wouldn't want to rely on it completely. There's maintenance issues as well, obviously, as well. If these things aren't maintained, they can seize up. If any sort of, especially on coastal areas, if that sand builds up and then just, sort of builds up against the flap gate or whatever, then physically it's not going to open. So there's a lot of maintenance issues around there. The short answer is yes, we need to incorporate sea level rise in any backflow prevention design. And then it's really just about probability. It's, what are the chances that design storm hits at the same time as a storm surge or a king tide? And that becomes a bit of an engineering judgment that we've got to make.
Cool. Comment from Alex Gutkin from WSP in Melbourne. He says, excellent presentation, Sean. The best one I saw over the years. So very well done.
Thank you.
We love a bit of, praise on this webinar series, don't we?
Yeah, thank you.
Winston Boone from Inertia Engineering in Brisbane. Keeping the praise coming, he says, always great to attend your webinars, Sean. He asks, what are your thoughts on when councils will start to adopt the incorporation of 2100 sea level rise, especially in detention modelling? I know Noosa has started to incorporate this. However, when do you think legislation will be more strict in taking this on?
Oh, that's a good question. I don't know if I can answer that on behalf of the industry, but look, yeah, there are councils that are definitely incorporating sea level rise. I'm pretty sure Brisbane City Council did this quite a few years ago now. It might have been maybe 3 or 4 years ago. There was, don't quote me, but I think it was like an 800 mil increase in sea levels. Obviously, that's going to change anywhere around Australia that we're working. Look, my opinion would be that we're probably have to incorporate it now just on the basis of being a professional engineer and providing an engineering service and being aware of all the science and the research that's there. We know these things exist. And so, in my opinion, if you don't incorporate it into your design, you're being negligent. And I think that's how maybe courts will see it as well. If we're ever pulled in front of a judge and explained why we made things, undersized when we knew about climate change as well. Planning scheme policies will always be lagging behind because they're only updated every 10 years or so. And it's no fault, it's just the way it is. And so they won't be able to incorporate a lot of things on climate change, unless of course there's temporary local planning instruments, and then that gets in the whole planning realm, which I'm not experienced in. But yeah, so there might be some ways to try and incorporate it, but really you've got to just wait for that planning scheme to update. So yeah, I think it really rests on the engineer that's actually signing off on the work, and what risks they might be mitigating, or what risks they might actually allow to sort of go through to the community, and whether that's acceptable or not.
Cool. Another question. We've got lots of questions, so I'll dive straight into them. Alice Chapman from Lithgow Council asks, are there any guidelines local councils can use for best practice methods on increasing climate change resilience in stormwater engineering?
Yeah, I think because it's such a new, content, new research that's coming out, no one's really got to that stage where we can put together a bit of a guideline, a hard and fast, set of rules to actually adopt. I think the whole industry is really just scrambling to try and get our head around how to, best tackle the problem, I suppose. Yeah, I don't know what else to say to that. I think it's just, listening to everyone around the industry, talking to each other, especially councils, talking to different LGAs and seeing what they're doing. Certainly something that we find when I host, training for different councils. We'll just talk about what other councils are doing, and then I'll, tell them to go and talk to a certain other council, not even locally, but in different states. So we do try to do that, and we just try to network people to just keep that conversation going. And then, once they find out information, bring it back to the community as well, and share it, because we're all, I think, on this journey together, and we're all sort of trying to deal with it at the same time.
Thank you, Sean. Darren Evans from Brisbane City Council just chimed in with a comment saying Brisbane City Council adopted predicted sea level rises by 2100 into their planning scheme in 2014.
Oh, it was longer than I thought.
Yeah,
10 years ago.
I think other councils that I remember a few other Queensland councils adopted at the same time. And I remember thinking there's planning scheme requirements around climate change, but then the state government at the time were actually denying climate change. So anyway, we'll move on. Yelena Shrep asks, using ARR Data Hub, climate change rainfall factors, what approach would you recommend designers should take when applying those? Worst case scenario / best case scenario checks? Do Drains, XP Storm, or any other software have a way of converting rainfall data based on those climate factors? Or is there another workaround?
Yep. So the climate change, so we're looking at Australian Rainfall and Runoff Guidelines, and I think it was, I forget the chapter, I won't quote it because I get it wrong, but there's a chapter in there in the guidelines about climate change. They were updated sort of towards the end of last year, I believe. So before that, there was just one climate change factor that we could apply. So it's easy to apply to all sorts of different software that we were using. You take the rainfall intensity and you just crank it up based on that factor. Since that recent update at the end of last year, those climate change factors, and you'll see in the presentation that we just had then as well, the climate change factors change depending on the storm burst duration, as well as the different scenarios. So it becomes a little bit more tricky to try and augment your rainfall intensities. It's not hard. Anyone can do it with Excel. You can get your factors and your durations. You can get your IFD table, and then just by selecting what storm you're using, you could find out what that factor is. I know Watercom, who produced the drain software, they had a webinar, might have been last week or the week before. They've got a new tool, and I believe it's free as well. Anyone can basically jump online and use it, and they'll take your IFD data, and they'll multiply by the suitable climate change factors as well. So they kind of do the hard work for you. But yeah, anyone can do it. It's very simple to calculate, and I'm happy to take it offline for anyone who wants to have a bit of a session or a sit down. We can sort of talk through how we do that. So yes, that's how you would do it. Yeah.
Might be a similar question. Cameron Scott from City of Bunbury in WA. We're dialing from all over. I see people in Tassie, WA, everywhere, all over. Cameron asks, are there any Excel spreadsheets? Engineers love a good spreadsheet, as you know, Sean. Are there any Excel spreadsheets? Are there any Excel spreadsheets that are available to summarize the methodology for storm estimation? Ones which allow inputs relevant to our area be put into accurate estimate storm volumes.
I think we're getting to a stage when we start talking about stormwater volumes, so detention sizing, that sort of thing. I think we're going beyond the capabilities of a spreadsheet, in the sense that I'm not saying that you couldn't do it. You probably could, but because we've got so many variables, for example, the ensemble method, we're looking at 10 temporal patterns for every duration for every AEP. So typically on a simple detention basin for a residential site, we're looking at modeling, 200 to 300 storms. So that's where I think the spreadsheets kind of hit a bit of a limit, and it just becomes too hard to practically go through. There's lots of different software out there that can do it, which will probably work a lot better. Having said that, there are sort of some pretty rough rules of thumb that you could use, but I'd probably steer towards getting the stormwater software to actually crunch the numbers. Nowadays, you'll be able to take any sort of a catchment and size up a detention basin. In our workshops, I think we're able to do it within probably an hour, 2 hours maybe, and that's teaching someone. So once you've got that experience, you'll be able to knock up a detention basin sizing within your lunch break sort of thing. So there are really quick ways of doing it nowadays, thanks to software.
And thanks to wonderful training providers like you, Sean. Question from Hector Salgado, he has the best name here today. He's from WSP in Perth, I believe. Hector asks, with the introduction of the new climate change factor, all new developments we design will need to account for increased capacity. However, if we connect to an existing network that has not been designed with this factor in mind, it may now be undersized. Could this create any issues?
Absolutely. It creates a lot of issues. And this is what we're struggling with at the moment. The industry, it's easy enough for us to just design for climate change, even though that's a bit of an estimate and there's a lot of variables in there. That's the easy part. The hard part is looking at our existing infrastructure and seeing how that's going to survive with climate change going forward. So yes, it 100% does cause issues. I mean, just from an engineering standpoint, there's issues because yes, you've got this bottleneck that you're sort of getting choked at the end of your proposed design. But the other issue, which I think is going to be far more difficult, will be developers that will say, well, why do we have to size this stuff so big when right down the street, they've got these tiny piddly pipes. I don't want to do it. Or the subdivision that was approved last year didn't have to do this climate change stuff. You're too conservative. Yeah, I'm going to basically push back and we don't want to do it. The other thing is the planning scheme policies aren't up to date. They don't update overnight. So the other thing that a lot of people will push back for is to say that, well, the planning scheme doesn't say we have to do it. So we don't want to pay for that. And then depending on how the industry is, if we're all, scrambling for work, they'll basically say, well, Sean, you're too conservative. You're crazy. You're talking all this climate change nonsense. I'm going to go with this other engineer that's half the price, sizes everything a quarter of the size and save me a bunch of money. I think that's going to be our biggest challenge going forward. And then really, in my opinion, the way that we can overcome not so much the political side, but just the engineering side, we've got to look at our existing infrastructure and we've got to model what will happen with climate change and accept that in most cases, we will be flooded, we will be inundated, we will have more bushfires, we will have all these other things, but we've got to look back to resilience and see how can we build in resilience into that design? How can we at least protect the infrastructure maybe for a certain amount of time? Or more importantly, how do we protect the community? How do we get flood evacuation, emergency management sort of systems in place? leverage the power of GIS to be able to incorporate all of this and give out early warnings, so we can protect people, knowing that the infrastructure is going to go under, and then bring people back. Yeah, I think resilient, that's probably the best answer going forward.
Yeah. And we're often talking about pits and pipes and basins and whatever, but I think of water quality or stormwater assets, water sensitive urban design assets, bioretention. And I remember I have a podcast chat with Dr. Tom Remini from Tasmania just recently, and the prediction is essentially a 7 to 8 degree average land temperature increase in Australia, 7 to 8 degrees hotter in 75 years' time, which isn't that long away. And you think they just had assets, bioretention systems, how could they cope with that much more extreme heat, longer droughts, in more intense rainfalls? But yeah, the buzzword for the day is resilience, but what does that even mean? Anyway, the questions keep coming through. Sorry, Sean. Another question from Rowan from East Gippsland. He asks, after what catchment size should we go for routing method rather than rational method?
So I won't be able to memorize this off the top of my head, but in the Australian Rainfall and Runoff guidelines, if you flick me an email, I'll flick you a copy of it straight away. But they've got this neat little diagram that has all the different hydrological models, and it's based on the size or the scale of your catchment. So essentially, in the ARR guidelines, for example, the rational method, they typically say that should be like a single lot or a 2-lot size scale. So it's very limited. We shouldn't be using that for anything bigger than, pit and pipe design, essentially. Then after that, then you get into runoff routing, time area methods, and then it keeps going out until you go right into Monte Carlo simulations for massive scale sort of models. I can't remember off the top of my head, but send me an email and I'll definitely flick you a copy of that.
I'm just conscious of time. We actually have just tipped over the magical 1 hour mark, but we've got 212 people already still hanging on to every word that you're saying, Sean. So just a reminder, folks, we're going to keep on trucking along with just getting through these questions, and there's still a fair few. But if you need to skedaddle back to work, whatever you might need to do, the recording will be made available on the Ocean Protect website in about a day or two, just under webinars, as per all our webinars. But we'll keep on trucking. Righto, a question from Nadia Ayub. Are there any guidelines suggesting which SSP or RCP to apply specific to the design of pit and pipe or basins for highways/urban development projects?
There's no, from what I've seen, there's no hard and fast rule or direction as to what to be adopted. And I think the reason why is because it's just such a big unknown. We don't know which way we're going to go going forward. In my opinion, I think the way that we should be looking at it is, unfortunately, means more work for us. But I think we should be looking at a range of different scenarios, so different extremes from most optimistic to maybe most pessimistic, and just see what that looks like for your design. And then you'll be able to have a bit of an engineering judgment as to the sensitivity, I suppose, of what might actually happen, and then assess the risk. A lot of the engineering work that we do now is very much risk-based, especially in stormwater engineering. It's all risk-based. It's no longer, this is your Q100 flow rate, this is your flood level right up to this point, and if we build 300 mil above it, we're all safe. That doesn't work anymore. And so when we do that sensitivity analysis, we can say, well, your building's going to be here and your flood might be here, or it might be well and truly above, and let's assess what would happen in each of those scenarios. So no, not that I know of. I think it's more just an engineering judgment as to at least put all the facts out there, and then between the engineer, the client, and council, for example, come up to something that we feel is a risk that we're happy to live with, I suppose, going forward.
There really seems like there's some clear need for some guidance, more guidance and tools around this issue, but we'll keep on, hence all these questions. Another one from Craig Hopf from Sydney in New South Wales asks, how do we know we're actually going to get more rain from climate change? Is it through interpolation of existing increases and predicting these increases will continue, or something else?
Yeah, I mean, even just looking at the last 10 to 15 years, we're seeing much more severe storms happening much more frequently. And so like, not even like a Q100 or a 100-year storm, but even a 20-year or 50-year storms, they're happening in the same locations. So say Southeast Queensland, for example, they're happening much more frequent than every 20 years or every 50 years. It's every 7 years, 3 years, 8 years, and so on. So just over the last decade, we've definitely seen that firsthand. All the historical data that we've shown, obviously it's statistics. So there's a very big, especially when it comes to rare storms, there's a very big variance in what might actually happen. But really, I think the evidence is pretty clear. It's there. We're seeing it day in, day out, not just in Australia, but all over the world. We're just having, it's just these really short, super intense storms that are dropping a stupid amount of rain. And all our infrastructure is not built for it, basically. Yeah.
And just physically, we know with higher temperatures, the atmosphere has a greater ability to dump rainfall, obviously, as well.
Yes, that's right. Yeah, exactly. Yeah, a lot of it is just pure science, right? Like the air warms up, there's more water vapor in the atmosphere. It comes up and basically just cools down and drops. Yeah.
Random question: is Brad Dalrymple related to the famous historian William Dalrymple? Who knows? I do know William Dalrymple, but only as a fan. So yeah, he's a super famous Dalrymple, but he's standing in my shadow. Clearly, isn't that right, Sean? Is that right?
Well, we need 2 photos, Brad. I need to see if there's a resemblance or something.
Amir, a question from Amir Degani. They say, thanks for the nice presentation. How can the burst portion of the storm be specified?
Oh, that's getting a bit above my expertise. So from what I understand, with all the statistical analysis, there are certain thresholds with regards to like the rainfall intensity, and then once it hits that threshold, then it's classified as that storm burst, if you like. Otherwise, it'll be classified as your pre-burst or your post-burst. I don't know the exact threshold or process or model that's used. But it's all in that statistical analysis that a whole bunch of mathematicians and hydrologists would be doing in the back end.
Rob Booker from Sunshine Coast Council has been very patient. Rob asks, do you think the QDM minor system criteria needs revising with these substantially increased rainfall intensities due to climate change? For instance, when it is not safe to drive due to lack of visibility during a 39% AEP rainfall event under projected 2100 climate, and minor system is for people driving on the road. When is it? Oh, sorry, get that. When is it not safe?
Yes,
to drive under those conditions. Sorry,
I think I know what you mean.
It's a long question. Sorry.
It's interesting. It's I think the terminology's definitely got to change, because now our 1% storm, so a 1 in 100 year. I hate using that terminology, but a 100-year storm that would happen. 50 years ago, it would kind of fall every 100 years or on average. Now we're seeing that's now becoming more like every 50 years, every 20 years, and it's just getting smaller and smaller. So you either have to change the rainfall information and factoring it up, like we were looking at with the climate change factors. And so now your rainfall intensity is completely different to what we were using a couple of decades ago. Or you change the storm frequencies that we're designing to. So instead of your pipe now that was designed for a 39% AEP, so a minor Q2 event, to keep the same pipe size, maybe we have to design for, instead of a Q2, we're designing for a Q1 event. And we've got to accept that we're just designing for smaller storms. Or we have to design for the larger storms and apply the factor. There's no clear-cut answer, I don't think, and I'm not sure what we're doing, but currently the industry right now is the best we can do is just apply a factor to the rainfall intensity and still adopt all the terminology that we've used in the past. So a 1% storm's your major, 39% storm's your minor for your pit and pipe and that sort of thing. The other thing to keep in note is, like, when we start changing all the terminology and the wording and frequency and everything else, we've got to come back to practically what's happening. And the rainfall on your windscreen is a really good example. I forget what the intensity is, but it's like 130 mil an hour or something. When you get a certain amount of rain that's coming down, There's been studies where you just can't see in front of your window. So regardless of what we call it, we've still got to go back practically and say, well, this is the amount of rainfall that's coming down, and we've got to make sure that our roads are safe or that our infrastructure can take those certain flows. So to not answer any of your questions is basically we're not sure. We're not sure how we're going to update that.
I'm still being bombarded with questions. And just a reminder, folks, if you want to ask Sean a question that we don't get to today, and there's plenty, please just reach out to Sean directly. But I'm going to give the last question to Rowan from East Gippsland because he wants to close this out. So we can't, backflow devices. Yeah, it's debatable whether they're good or not. Around trying to mitigate sea level rise. So he asks, can you share some ideas how we can design a stormwater system considering sea level rise?
Yep. Again, in my opinion, the easiest way is to make sure that you've got overland flow paths, essentially. So if you were to just take out all of the underground stormwater infrastructure, if it was completely blocked, closed, not working, analyze where the water is going to go when it does surcharge out of your pits and pipes, for example, and see where that water is going to go until eventually it tips out somewhere. That's ultimately the best way to do it. Anytime I've trained engineers and designers in the past, I've always said whenever we design any storm infrastructure, we always go straight to the major storm, ignore all the minor storm conveyance, just as your first pass, your concept, and just make sure all that water can actually get out as overland flow. And that way, it'll allow me to sleep at night once I sign it off. But it just gives you more confidence. So when that minor system does become inundated or overcapacity, there's still an outlet for it.
Cool. Well done, Sean. Your voice is still holding together, which is a great outcome. And just a reminder, folks, if I didn't get to your question or just wanted to just talk to Sean separately, please do so. These contact details are all on the slide there. But just a final word of thanks. So thank you so much for everyone who's dialed in today. Another super popular session, and also a big thank you to Sean for giving up his time today and sharing his pearls of wisdom around all things rainfall and beyond, with a particular focus on climate change in the end. So, and just a reminder, folks, the slides and the recording will be made available on our oceanprotect.com.au website, just on there. You'll get a CPD form in the very near future. If you don't receive it in a week, just feel free to drop us a line at marketing@oceanprotect.com.au. But yeah, and just a reminder, we've also got our next webinars next month, presented by Murray Powell from Optimal Stormwater, talking about the design of primary stormwater treatment assets. So looking forward to that, and probably a very yellow jacket, courtesy of Murray. So again, thanks so much for Sean today, and thanks everyone for attending. Enjoy the rest of your day.
Thanks, Brad. Thanks, everyone. We'll talk soon. Cheers.
Bye for now.